have our second test coming up Thursday, and today's a review day, so we're going to go through some of them. I compared to the exam, which I do have ready to go. And so we'll take a look at a few examples. If you've got questions, we'll get those answered as well. And keep moving forward. You will be able to continue to work on homework, but again, I guess at this point, the best thing to do is work on the reviews. Get yourself ready for the test. And, homework's still good, but don't let that get in your way of studying for the test. So kind of get the overview. We'll continue to work. In this class, this is our last one before the final, or do we have one more? We had 2 tests and then the final, right? I think my other class we have 3, so there's one more. Anyway, continue to work as best you can. The final is comprehensive, so that gives me another measurement of how you've done on the whole class. So if you didn't do as well as you'd like on 1 or 2, I can always look back and say, by the end of the course, you have learned it. So keep moving forward, and all will be good. Let's see. I saw right away is let's go with this. Was this question here? We haven't done an example like that in class, have we? Was there one on the homework that was similar to this, or one in recitation? Probably not. It's kind of strange, but you'll need to know how to do this one, so we'll go through this as a start. So it's a very important one. It's exponential, but what you have to see, it's got a quadratic, so there's a 2x and an x. What you really want to see this one is, and I'll just take up all the space here, you want to see this as 7x squared, because exponent to an exponent, you multiply, right? So 2 times x, we can do it this way, plus 2 times 7x minus 15 equals 0. Then what you want to do is you want to first solve this as if it were like a quadratic. So what I'm going to do is I'm going to replace this 7x. Let's just kind of put a variable in there. And in math, a lot of times when we want to kind of put something that's, instead of putting x, because we got 7x, we'll just call it u for now, and I want you to see it. When we go to solve this, it's going to be like u squared plus 2u minus 15. And if that's what we had, how would we do that? It's quadratic, equal to 0. Factor it, right? So we're going to factor it this way, and then we'll back substitute for the 7x and be able to solve it from there. So this u squared plus 2u minus 15, it factors into, 15 is 3 times 5. And if you subtract 3 and 5, you get 2. So we should have, and the plus is on 2, so that means the bigger one, 3 times 5. 5 is bigger than 3, so this should be u plus 5 times u minus 3. So that's sort of the first step. So put in some kind of a substitution there, do a quadratic factoring, and then what do we know? What this tells us is that since these two are equal to 0, and we're multiplying them, let me turn off my blue. I know you guys don't hear it, but I got somebody in my head, this little thing talking. So when two things multiply to give us 0, then one of them has to be 0, right? That's the only way to multiply and get equal to 0. One has to be 0. So we know that either u plus 5 equals 0. So we'll do that up here. Or u minus 3 equals 0. So now at this time, where did u come from? We made it up, but what was it? It's 7x, 7 to the x. So that's where we could kind of replace it now. We could say this really is 7x plus 5 equals 0, or 7x minus 3 equals 0. So subtract 5 from both sides over here. You get 7x equals negative 5. And if we've got this exponential, how do we solve for x here? What's that?
You put the negative 5 above 7 and it equal x.
Negative 5.
Don't you flip the x and negative 5 to try to solve them?
Okay, you've got the right idea. Yeah, so we do the log dance. So we turn it into a logarithm. We could do this as, okay, gotcha. Log base 7 of negative 5 equals x. But do we have a problem here? Can you take the log of a negative number? We can't. So while it leads to an answer, it leads to an undefined answer. So that part's not going to be the solution. Okay, so sometimes that's what happens with exponentials or logarithms. We get a solution, but it don't work. So negative, whatever this is, it's not going to work. Where we're going to get the solution is when we do the same thing over here. So we'll add 3 to both sides. You get 7x equals positive 3. Now we do the same thing, use logarithms. And again, you could take the natural log of both sides if you want to do it that way. I just like to do the sort of log dance and do a log base 7. So this becomes log base 7 of 3. That's what you meant by the switch, right? Equals x. Notice that solves it for us. We have a value for x. And then this is an answer. It is a solution. Log base 7 of 3 is a number, right? If they want, and it is an exact number. So if the question says to give an exact number, we're done. If it's in the multiple choice, you look for that. If they have a decimal number, what they did is they plugged it into a calculator. If they have this would be the answer, right? So in the open answer, if it's just like give us an answer, I'd accept that because that is an exact answer. However, to really figure out what it is, what we do is we come down to our, let me get my graphing calculator. Oops, not there. And please be patient with me on the grading. I just gave 2 exams for my MAT171, so there's 200 exams to grade by this weekend. We'll have yours on Thursday. And at the community college, I've got giving 2 exams. This is exam week. So a bunch of exams. I'll do my best to get them all done over the weekend, but it might be late in the weekend before it gets there. But we'll get you all set up. Let's see. Let's get this. And so we could just go to second quit, just get to the calculation screen. Remember, you can do a general logarithm if you just, at least on the TI-84, if you go to the math key and then go down, and there's something called log base. And we're going to do log base, and it lets us put in log base 7 of 3. Enter, and that's its answer. It's 0.56, so it's a little bit bigger than a half, right? But that would be the decimal equivalent. Just depends on how they ask it, what they want. Both are correct answers. 0.5646. We'll round it to 4 decimal places. Okay. So those are the 2 correct answers. This one over here leads us to something that's undefined. Either one of these would be acceptable answers. But that's the tricky one. So look for it. It might not be 7 to the x. It might be some other base, but you're going to have, there will be one like this that is quadratic in form, that you have to turn it into, just solve the quadratic by factoring. But when you go, once you've got that quadratic, put the exponential back in. Okay. And that's one I want to directly address because we have not done I haven't done an example like that. Was there one in the homework? I don't remember seeing one in the homework, so I thought, when I looked at the test, I go, really? And then I looked at the practice test. Okay, they've got one here, so that's the first one I'm going to highlight for you. Remember, there is also the answer key, not just an answer key, but a solution guide. So the coordinator went through and she worked through with color pencils and stuff and has everything worked out. So go to that link. So right below the review, there is that link that will take you all the way through it. We good with this? Does that make sense? So convert it to a quadratic, factor it, and then solve each little piece, and then that's the only way to do those. Let me clear this out. Do you want to see either of those two? Either the other two? The first one. Okay. So A. Again, we could do this by taking the natural log of both sides. If you want to do that sort of thing, you could. You could also, since it's just an exponential equals a number, you could do the log dance. 2 is the base of the exponential. This is the way I sort of prefer to do it. Because our calculators, as long as you have the log base, I would do it this way. If your calculator doesn't have the ability to do log base, then maybe natural log is a little clearer. And I think it might be the way the text does it. So this is log base 2 of 8, right? That's just a number. And actually it's kind of a nice number, equals 2x plus 17. I would check to see if log base 2 of 8 is a good number, and it is, because 8 is 2 to the third power. So you're going to see log base 2 of 8 is equal to 3. And if you weren't sure, just pull up your calculator. We go to math. Oh, clear. Math. We'll go to log base. I was told by a student if you go up arrow, you get there quicker. Come from the bottom side, and we'll do log base 2 of 8. We're going to see that's equal to 3. Nice number. 3. So we just replace the logarithm's now gone. Log base 2 of 8 is equal to 3, so we get 3 equals 2x plus 17. Now have just a linear equation, solve for x, right? So it's much nicer, no logarithms to deal with or anything. If you do the natural log, then you're stuck with those natural logs, because natural log of 2 and natural log of 8, it would still all work out the same way, but let's just do this. So we would subtract 17 from both sides. 17, 3 is negative 14. Equals 2x. Divide both sides by 2, so it looks like we'll get x equals to negative 7. Negative 14 divided by 2. That good? Sometimes they look, yeah, I always think that one looked a little ugly, but it worked out okay because of the numbers. While we're here, this other one, we could do the same thing. This one will be a little ugly because you got a base 3 and a base 7, so it's not going to work real nicely either way. This is one I would go ahead and use natural log on both sides. So we take the natural log of both sides, so natural log of 3x equals natural log of 7, 2 minus x. We use that property of logarithms that if you have the log of a number and it's got an exponent, the exponent comes down and multiplies in front. So this gives us x natural log of 3 equals 2 minus x. Now be careful here. I see some of my, in the business calc, sometimes they won't put this parentheses, but you've got to. The whole exponent comes down and you get natural log of 7. So it's not real nice, but what we can do is, what you would do at this point, get the natural logs. We've got to solve for x, right? So let's divide by x. And then, well, that's what I might need to move Okay, oh, I get some room there. So the x is canceled here. We have natural log of 3. I'm going to, since these two things are multiplied, I'm going to divide this fraction, and this will be, how do we want to do this? Well, this becomes 2 minus x over x, natural log of 7. Divide both sides by natural log of 7. When we divide it here, this becomes 1. So I'm just, to save myself some room, I'm going to erase this. Natural log of 7 divided by natural log of 7. Right? So that's 1. And then, now remember, this is just a number, but it's not going to be a pretty number. It's going to be some decimal. That's as exact as we can get it. Jeez. Well, you can distribute this x, both dividing, right? So if you do that, let me erase the other one. I'm going to give myself some room. Remember, this will all be recorded. I'll get this posted as soon as I can, potentially still today, so that you can review it as need be. So I would do, wait, I erased natural log of 7. I can't do that. So we get natural log of 3 divided by natural log of 7 equals 2 over x minus x divided by x, which is 1. Okay, you can add 1 to both sides. Yeah, where did plus 2 come from? Oh, I started looking at the 2 when I was thinking of writing the 1. See, this is how mistakes happen real easily, right? While you're multitasking. While you're trying to write something, you're looking at the other side. So that's how it happened. I haven't quite solved for x yet, but it's not real pretty, is it? I guess the easiest way to do this would be multiply both sides by x. Maybe I should have gone the other way, but yeah, I probably should have divided by 2 minus x. It would have been simpler, but the x cancels here. I'm not actually going to multiply this out. What I'm then going to do is divide by this part. So notice the x's have canceled here. So they're gone. I'm going to end up with x equals 2 divided by all of this. And again, if they want it as a decimal, we could plug that in a calculator, calculate it out. If it's in one of the open answer type questions, this is the exact answer. This is as good as we can get. I'd accept to just leave it like that. Okay. Otherwise, see if I can. We would put it in here as 2 divided by, I'm going to put a parentheses. Where's my natural log? Natural log of 3 divided by natural log of 7 plus 1 with the parentheses. So I've got the whole denominator in the parentheses, and we'll see it'll give us a number. Again, not a, yes, sir.
So when you divided the x, what happened when you divided the ln 7 by x?
Because we're multiplying two things,
Right.
so we've got two factors, it didn't distribute to those. It only distributes over addition. So what I did is I grouped it here. Oops. Let me do it this way. So I'm seeing this as a group. I then divided both sides by natural log of 7, so that canceled out here. So I divided by, so that canceled. And because it's multiplication, we can do that. If it was addition, you're right, it would have to distribute to it. But because it's multiplication, we just group it here, and so that's why I got this part, natural log of 3 over natural log of 7. Good question. And again, if there's a few in the open answer, I'm not sure if they'll be like that, but just show all your work and we'll go through. Other questions? All right. Let me clear this out and we'll, we got a little bit. So I just want to go over kind of, so there'll be these logarithmic type equations as well. So solve exponentials like we just did. That I definitely want to do that one with the quadratic. These ones you're going to need to use properties of logarithms to get it down to one logarithm, and then you'll change them to exponentials to be able to solve them. So if we've got exponentials, we get them into, if we have exponentials, we change them to logarithms. That's the way we've been solving it. We have logarithms, we use our properties, get it down to a single logarithm, and then use exponentials. Would you like to see maybe one of these? And then, which one? Any preference? Tried to pick the hardest one? Anybody?
C.
C. Yeah, that's the one I'd probably go for. So on C, notice we've got subtraction here. And we've got two logarithms. They have the same base, which is important. So we can rewrite this as log base 2. When we're subtracting, we divide the two, right? So this is going to become x minus 3 over 5x minus 1 equals 4. Okay, so that's the first step, get it down to that. Then to solve it, we do the log dance, we change it into an exponential. So the base is 2, the exponent is going to be 4, and that equals x minus 3 over 5x minus 1. And now we solve from there. So notice the logarithm is completely gone. Now we're going back and doing, I think we did these earlier with rational functions, right? 2 to the 4th is 16. 2 times 2 is 4, 8, 16. Okay, so we'll do that. That's going to be 16. And at the same time, let's multiply by 5x minus 1. We could distribute that 16. I think that'll probably be the best. So 16 times 5 is 50 plus 30 is 80. 80x minus 16, so notice I just distribute, equals x minus 3. Subtract x from both sides. So I get 79x I guess at the same time I could add 16 to both sides. And you might want to do that in 2 steps. I like to just save some writing. Negative 3 plus 16 is going to be 13. This, and then we would divide both sides by 79. So x equals 13 over 79. Does 13 go into 79? Anybody? No?
When I did that way, when you scroll down, you get a different answer. You got 19 something. 19 or something.
Let me make sure. 2 to the 4th is 16. 16 times 5 is 80. Let's make sure I copied everything down right. This was number 8. Go down to the answers. 19 over 2.
Oh, no, we got no solution first.
Yeah,
To see.
Oh, sorry. Oh, a C, no solution. Well, we aren't done quite yet, because we've got to see, once we get it. See, where were we? We're here. Let's see. 79 divided by 13. No, it doesn't go in there. But let's take 13 divided by 79. I come up with that this is going to be 0.16. What we need to, on these ones, what you always need to do is come back to the original and plug it back in. So notice if we plug it in here, log 2, you'll have 0.16 minus 3. We're going to get a negative number, right? And you can't have negatives inside a logarithm. Don't even have to check the other one. The other one would be probably might be okay, maybe not. But we've got a negative here. If you got one part that's undefined, everything's undefined. So then we say no solution. If you left it there, I'd say, okay, you got to that part, you just forgot, so you'd get most of the points, but maybe not all. Let me show you one other way of doing this. So I'll do it. You could also, any equation, you can graph both sides. One is y1 and one is y2, and then what you're looking for is where they intersect. What we'll see here is when we look at the two graphs, we won't see any intersection. So let me pull up the graphing calculator. Let's go to y equals. And let's put in log base 2 of 3. So I'll do log base 2 of x minus 3, right? And then we had minus log base 2 of 5x minus 1. So that was the left side. On the right side we have 4. And let me go to zoom standard 6. And we can kind of see you've got one down, the blue one's down there. If it's going to intersect, it's going to be like way out there. Let's see. Take our window, make our x max maybe 500. See if we get far enough out. It don't look like it's going to intersect, do they? That's what no solution looks like. The two lines never meet. Okay? And again, you could do it algebraically like we did, and we get that number. We got a number by, but that's because it was no longer logarithm. We always have to go back and check when you're dealing with logarithms. Check that your answer produces something that's defined. Just like when we have rationals, we can't have 0 in the denominator, right? We got to check if that ends up being our answer, no solution. So, but graphically is also a good way to you see it, right? Those things aren't touching. So that means no solution. Maybe use both of them if you can, but certainly the graphing method works. Okay, is that helpful? Sort of? Okay. What else you want to see? So let's clear that out. So solving logarithms, solving exponentials, some things on the domain. When you have an exponential and they're asking for its inverse, what is our inverse going to look like from an exponential? So what? You'll switch the x and the y, but what kind of a function are we going to end up with? A logarithm function. That's so part of it. So yeah, let's do maybe one of these. So yeah, we can rewrite the original function as y equals 5x minus 2 plus 1. Remember, this is all up here. We switch the x and y to get the inverse. So this becomes x, the y becomes x, the x becomes y. And we want to now solve this for y. We want to get to y equals, that will be the inverse. Well, how can we do this? Well, we have to isolate the exponential first, right? So we would subtract 1 from both sides. We get x minus 1. I'm going to group it like that. 5 to the y minus 2. And remember, we're going to get a logarithm. Where do we get it? It's at this step where we do the log dance. So we're going to change this exponential into a logarithm. So that's going to be log base 5. Remember, that's the logarithm's always going to have the base of the exponential. It's going to have the other input, x minus 1 equals y minus 2. But we're not quite done. What's the last thing? Because we're solving for y, we have to add 2 to both sides. So we get add 2. We're going to get log base 5 x minus 1 plus 2 equals y. This is our inverse function. So if you want to use inverse notation, g inverse of x equals log base 5 x minus 1 plus 2. They might ask about the asymptote. Remember, with logarithms, the standard logarithm graphs this way. So the asymptote is x equals 0. But this has been moved to the right one, right? X minus 1 moves it to the right one. So now our asymptote's not going to be 0. It's going to be x equals 1. Again, you could also just go ahead and so to answer this, x equals positive 1. And you could see that's if you plug in 1 minus 1 is 0. It's where the logarithm would be equal to 0. That's an asymptote because logarithms, you can't put negatives in there. You also can't put 0, but 0 is sort of that borderline. That's where the asymptote is. So you just kind of look x minus 1 equals 0, solve it. So does that help? And again, you could graph it, and you would see that oh, that's going down about 1, not at 0. Okay, so so be able to get an inverse, and just if it's an exponential, inverse is going to be log. If it's a log, the inverse is going to be exponential, because that's how it works. All right. What time is it? Okay. There's a couple word problem things here. Radioactive decay, population growth. So we have a growth factor, right? Population growing. We have radioactive decay. this one's nice. It does give us our function, find the half-life, estimate population, and then we get into this, start getting into the trig, so know how to find the arc length, right? And arc length is generally, there is a formula if you have degrees, but typically arc length, right, is they label it as S is arc length. I don't know why. Is R times theta or theta times R. But the theta needs to be in radians, not degrees. So be careful with something like this. Don't put 60 times 16. I mean, you're almost there. We have to change 60 degrees into radians. And how do we do that? Where are, what's that?
60 times
Pi over 180. So pi and 180 are a place. You could do 2 pi over 360, but it's the best place usually to use is that at pi, that's 180 degrees. And so notice the degrees will cancel out. So we get 60 pi over 180. 60, so that reduces, 6 goes into 18 3 times. This is pi over 3. Or if you remember that 60 degrees and pi over 3 are equal, you just go there. So our arc length is going to be pi over 3 times 16. So 16 pi over 3. And that's a perfectly good way to leave it. If they want decimal, take 16 times pi and divide by 3. You'll get some decimal equivalent, right?
I have a question.
Yes.
What does it mean by interpreted, like by the central angle?
There, basically, we always use the central angle. I'm not sure why we make such a distinction. Maybe because with triangles we have opposites, we have different sides. But when we're ever using a circle, the angle that we use is a central angle, meaning it comes from here. In using circle, I wouldn't know what another angle looked like. I guess you could, I guess, get other angles, but that's all it's referring to is that the angle's coming from there. So that we've got that this is the 60 degrees they're referring to, or like we say, we convert it to pi over 3 to get arc length. Because that's how radians are measured, right? They're really arc lengths. You good with that? Try to get you some caveats. And the length of an arc on a circle of radius 10 centimeters is 20 centimeters. Find the measure of the central angle in degrees. Again, you would use this formula, S equals theta R. We know that the radius is 10, and radius 10 centimeters is 20 centimeters. So the arc length is 20. The radius is 10. So you divide by 10. 2 divided by 10, you're going to get, or 20 divided by 10, you're going to get 2 is equal to theta. But remember, that's not degrees, right? That 2 is not 2 degrees. That's 2 radians, because there's no degree marker. So now we got to convert that to degrees. How do we convert? See if I can go up a little bit. Can't. How do we convert radians to degrees? Let me do it up here since I ran out of room. So 2 is radians. We need to divide out the radians, which is pi, and multiply by 180 degrees. So now that's going to give us degrees. So we get a weird number here. 2 times 180 is 360 degrees divided by pi. I guess we could just go like this. You could then take 360 divided by pi, and what do we get? And I'll use the pi key just to get it as accurate as I can. This is going to give us, should give us 114.5 0.59, so maybe 0.6, I rounded up degrees. They don't say what to, is that about right? Again, remember, you have the answers to all these. You also have the solution guide that will take you step by step, but sometimes hearing things and seeing some things is helpful. All right? Because we don't really have time to work all the way through this. Let me go back to the beginning part and see if there's any questions. Well, let me also open it. Does anyone have, after working through this before or looking through this, have any specific questions on any of the review questions that you might want to look at? Yes, sir.
Do we have to memorize the compound formulas?
Good question. I can't remember, so we're going to take a look. So along with this, there is, come on, here we go. I should have started off here. So exam 2, there is this review. There's review solutions. I also put the formula sheets. This is the cover page for the exam. Wait, where is it? Oh, here it is. Cover sheet. And also, I just want to highlight, we give you a template for the unit circle, but it's not filled in. You're going to have to be able to do it. If you watch this video, it's about 22 minutes. You could maybe do it double speed or something. I show you how to go through all of those, and again, how to remember the various coordinates and basically just count 1, 2, 3. Someone showed me that, because each coordinate, if you use your hand, you got 0 degrees, 90 degrees, and here's 30, 45, 60, and you can kind of count off that way as well. But the cover sheet here, let's see. You're going to have these formulas, so those are the things you don't need to memorize because you're going to have those. We give those to you. Does that help? So yeah, you've got the compound interest, you've got the continuous, you've got this exponential growth, you've got a few of the trig functions, identities, and that's all you get. And then you've got this little template. You don't have to fill it in, but it's there to, if you'd like to, it might help with some of the answers. What's that? Yeah, so we'll take a look. We'll keep going through the review to see, because I did compare the review and the exam, and every type of question that's in the exam is in the review. So focusing on that written review, you'll have worked every type of question anyway. On some of the word problems, I don't know if they do it for all of them, but they give you the picture. So sometimes that's helpful. In the review, they don't give you the picture, so you have to kind of set it up. They want it a little bit harder, but on the exam, they at least give you the picture, so it'll be a little bit easier to set up. We give you a template here. Yeah, so mostly I just want you to, the best thing is to work through this as many times as you can before Thursday, or at least one time, If you need to, look at the solution guide, and I'll just highlight that part. So the review solutions. So takes a while to load. So it's printed out or whatever, and there are the solutions done here. Again, you'll probably want it on a bigger screen to be able to see it and follow it, but you could kind of follow. It's been worked out. There are things over here that kind of what's going on. So these are some sort of notes, but she did go through and set them up. These are the formulas you'll need to use. This is how you do it. So they're all worked out here in multiple colors to make it a little easier to read. This one we just did, take the natural log of both sides, have these come down. So they're all solved out here as well, but they're static, right? So sometimes you're not sure what happened, how'd they go from here to here. It won't. But she showed a lot of steps. So I think she did a good job. So those are all here. Here's some, some graphs, and so notice it's been completely worked through. She does draw the picture, so if you have a difficulty with that, take a look at that picture. It'll help you set it up. But again, in the test, at least I know there's one where you have to do that kind of length of a pole type thing, and they'll set it up. You'll see it. But let's see. Yeah, here's same thing with the trig. So it's all in here anyway. So take a look at that. Use it as a study guide. And what's sometimes helpful, if you're kind of stuck and you're learning it, if you looked at the solutions, my suggestion is set it aside, wait a few hours, go do something else, come back and then do the review without the solution guide. Do it, and it'll be pretty much fresh, but you'll also be able to pull things back. But what that does, every time you think of something, there's a little track in your brain that gets made. That's how our brains grow. And so you slightly remember, but maybe not completely, but you have to think through it. It'll make that little pathway, those little electrodes, that much stronger, so that when you take the test, you do it. And if you have to look at that solution guide again and go through it, again, give yourself a break, go do something else, keep doing it until you can do it without having to go back to that, because during the test we won't have that resource. But use it, it's okay, but as much as you can. Okay, don't, because I see some students, they look, oh yeah, I know how to do that. But if you just saw it, you were doing it from the passenger seat, not the driver's seat. You got to be in the driver's seat, right? I always think I'm in the I'll remember how to get to my friend's house. But if I was in the passenger seat and I go to drive, I'll forget something important. But if I drive someplace one or two times, I'll remember how to get there. Okay, what else? Other questions? Doesn't have to be a specific question from the review, but it could be. Maybe if there's nothing specific, let's kind of go through. So you'll be able to have to write exponential equations in logarithmic form. So that's one thing. So do the log dance, right? Turn an exponential into a logarithm. Turn a logarithm into an exponential. Yes. Which one? 3D? B. 3B. Good. These are, and we're also going to have to use logarithm properties, something as messy as this. So that's good. Oh, geez. Okay. Yeah, you chose the fun one. When we're multiplying two things inside of a logarithm, what does that become? Adding of two logarithms. So that's the first thing I see here, is that we're multiplying two things. So this is, and then we got the natural log, so this is going to become the natural log of x minus 1 to the 3/2 power plus the natural log of this square root thing. But when we have a square root, what kind of an exponent is that? It is really the 1/2 power, right? 1 over 2. So I'm going to rewrite it that way, because that's when I'm using logarithms, that's a property. The exponents can come down and become multiplication. So I'm going to write this as, well, that. Okay. Next step is to sort of, we're still unpacking this stuff, is to get those exponents to go down in front. So I'm going to take the 3/2 and it will come down in front. I'm going to take the 1/2 and it's going to come down in front. So then we have 3/2 natural log of x minus 1. We are now done with that first one. It's been expanded as much as it can be expanded. Okay, there's not a property that x minus 1 now becomes division, or no, it's all that's in there. So that part's done. Over here, we're not quite done yet. We get the 1/2 natural log of y plus 3 over 4 divided by z over, or z to the 8th. When we have division inside of a logarithm, can we expand that? Yes, it's going to become two logarithms that are subtracted. Good. So I'm going to move over here. So we get our 3/2 natural log x minus 1. That's all done. What I'm going to do is I'm going to go plus 1/2. I'm going to put a parentheses or a bracket because now the inner stuff is going. You could put the 1/2 times each of them, but I just kind of like, we're working inside here, right? We're working in here. This now is going to become the natural log of y plus 3 to the 4th power minus natural log of z to the 8th. And it'd be nice if we were done, but we're not done yet. What do we have left to do? Those exponents have to come down in front. So now this 4 goes down here. This 8 goes there, and then we're done. So we got this long thing, and you could look at the answers, but it would have those in front. If you wanted to, you could distribute the 1/2 power, right? Let's see. Maybe so how about if I just, well, get that. I'm going to bring this 4 in front, but I'm also going to distribute this 1/2. So what's 4 divided by 2? 2. So you see how that happened? I took 4. I'm going to distribute the 1/2. That's 2 natural log y plus 3. The 8's going to come down, but then I've also got to distribute that 1/2. 8 divided by 2 is going to be 4 natural log of z. And I don't need those parentheses anymore. So that's what I got. Does that make sense? Does that help? Okay. So it's got a couple tricky ones in there, and again, the other ones that are expanded, and you have to put them back together. So they give you multiple logarithms with addition, subtraction. Subtraction is division. Addition is multiplication. So, practice through those. And hopefully, I don't think there's one quite as bad as that on the exam. I certainly hope not. A's not too bad. I mean, it's, addition, subtraction, but that one was kind of nasty, right? All right. Yes, sir.
So for number 4, do we have to distribute the 1/2, or can we just leave it as with the brackets?
Oh, like for number 4b?
Yes.
Good question. Let's. So let me. Is it okay if I clear this out? Yeah, so I was doing two things at the same time. So when the 4 came down, I was also distributing by this 1/2 that's in front. So I took 4 times 1/2, or 4 divided by 2. And I got the 2, and the same thing with the 8, because this distributes to the first term. It also distributes to the. Yes, and that's why I put that parentheses. That 1/2 applied to both of those terms. Good. Good question. So the question was, do I need to distribute this, the 1/2 here? Actually, on these, what you're going to do is those become exponents on just the term. So there's no multiplication here. Like this one doesn't have a half. Let's just kind of maybe do the first step. So we bring the exponent up here, and we bring this exponent up here. So we get natural log x plus 3 to the 3/2 minus the natural log of x. Nothing happened there. And then we put that 1/2 up there. But no distributing of it. Here's the thing is when we've got 3 terms put together like this, you can try, I've seen people do this, but you know, okay, this is subtraction, so this I'll divide, and then I'll do, if there's negative, the way I think of this is if there's a plus, that's multiplication in the top, that means it's in the numerator. If there's a negative, it means it's happening in the denominator. So what I would do is I would do this in one step. I would then just make it the natural log. This first one is positive, so that goes in the numerator. These next two are subtraction, so that means they go, both of them go into the denominator. And that's the final answer. Yes, sir.
Do I want to put the square roots in there?
You could, but you could also leave it as a, yeah, so if it's 1/2, you can make it into a square root, but you could also leave it as a 1/2 power. Yeah, it's perfectly correct. Now, again, if it's a multiple choice one, they might have done that, so you just have to say, oh, they changed them. I typically don't, because when we're doing algebra, and actually in calculus, we want it as a 1/2 power. That radical is like, it's a thorn in our side, because we're always having to change it back to do anything with it. And then we change it back just to make it look pretty, but I don't think it's that pretty. So, just leave it as a 1/2 is my preference. Personal, but it if it's your preference to go, it's still correct with the square root. And again, in a multiple choice situation, they might have the answer with square root, so then definitely you'd want to do that. But I would accept this, yeah, definitely. Bless you. Does that help? Yes.
In the solutions
Uh-huh.
that she did, she combined the 3 and the 2 and then the 1 negative 1/2. Did you do that?
Oh yeah, okay, they're the same. So yeah, you could do more algebra on it. I hadn't even looked at it that, yeah, so it's x plus 3 since they have the same base, right? It's like if we had, let me come over here. So if we had x squared and x to the first, and we had something else here, these can sort of cancel, just become x to the first power. So what she must have done, x plus 3 to the 3/2, you subtract the exponents, right? So final answer, and I've got to make my own key for the exam, so I probably would have stopped there, and then I would have come across yours, and you would have simplified. So, oh yeah, it can be simplified. So I would count both. But yeah, these would simplify. 3/2 minus a half is going to be 3 minus 1 is 2/2, right? 2/2 is 1. So it then would be x plus 3 to the 1 power over x. Thanks for mentioning that, because you might not say what happened there. Well, she just saw that, these x plus 3s are the same base, so we can subtract their exponents. Good. Thanks for keeping me honest. I get lazy and I say just leave it. Because it would graph exactly the same, right? But all right, good. Is that helpful? What else? Let's see. Let's keep going down. We'll see what we got. If you want to stop, we're getting close. We've got 15 minutes, but So compound monthly, compounded continuously. Remember, you do have those formulas on the formula sheet on the compound interest. So you don't have to memorize it, but know how to use it, right? Um, compounded quarterly for 5 years, accumulate. So again, compound interest. We did these. We did some of these. One of these. We talked about this one already. We did the inverse. And then there's these population growth models. I don't know if anyone have a question on 10? Yes.
Not on 10, but can you show how to show which quadrant cotangent less than 0 is?
Sure. So I'll just do it here. So if we know that cotangent
Greater than 0.
less than 0 or greater than 0. So less than 0 means it's going to be negative, and greater than 0 means it's going to be positive. What you want to think is cotangent is x over y. The coordinates are x over y. Cotangent's x over y. So in order to be negative, one of them has to be negative, the other has to be positive. So it would be a quadrant where x was negative but y was positive, or where x was positive or y was negative. Where's that going to happen? X is negative in the second and the third quadrant, but y is positive, and so it could be here in the second quadrant. I guess maybe I should change. So we know that cotangent is less than 0 in this quadrant, or it would happen where x is positive but y is negative. Well, x is positive either in the first or the fourth, but y is only negative in the fourth, so this would be the other part. And so it will be either the first or the fourth quadrant. Let's see, which way do we put it on? We put it over here. And then that, so once we've got the negative, it'll be positive in the other the other ones, right? It'll be either this. Wait, not first, second quadrant, second and fourth quadrant. So it would be the first and the third quadrant where it would be positive. First or third. Okay, but I always do that with all the functions, get them down in terms of x and y. Think of cosine theta as x, sine theta as y, at least on the unit circle, that's correct. And then all the other functions know, tangent's going to be y over x, cotangent x over y, cosecant is 1 over y, and secant is 1 over x, because they're tied together. Okay, be able to find the radioactive half-life. We did these with the angles, coterminal angles, positive angles, given these, so be able to do these. Given what cotangent's equal to a number, be able to find the other functions. Remember, that helps you set up that triangle. And which quadrant it's in, and then that'll help you find all the, so there, we did several of these type of questions. And then this poll question, again, there's one like that in the exam, but they will give you the picture, but be able to go through it, maybe go to the solution guide. We did a couple of these in class, I believe. Reference angles, finding the exact, so this 19 is where you would need the unit circle. Don't remember the unit circle, there's only going to be one question that really gets in your way, but I think you'll be okay. But yeah, there is a question on that, and that's it. So notice, yeah, there's only one question that directly needed the unit circle. And sometimes it seems like such a big deal to get that we overpower that. Anything else? Sure. Yeah. So we had a population of 20,000 in 1990, 25,000 in 1995. And then, let's see. Yeah, we got about 5 minutes. Find an exponential function that models population growth and use it to estimate the population in 2008. So what we can do is we make 1990 like year 0. So that gives us in year 0 we had 20,000. And so if that's year 0, what's 1995? Year 5. And we know in year 5 we had 25,000. And an exponential model we could use with population growth. A equals P use that one. Since we made 1990 year 0, this is our starting value, 20,000. That's our initial. Actually, I think they use A and A naught in the formula instead of P. We could do that, A naught. So then we've got our function so far is A equals 20,000 e to the RT. We use our second point. When we plug in 5 for t, our answer is now going to be 25,000. So we get 25,000 equals 20,000 e to the r times 5. 20, not 2,000, 20,000. I lost the 0. Take 25,000 divided by 20,000. And that should give us 2 point, let's see. That gives us 1.25. And I'm going to move the 5 in front of the r. Take the natural log of both sides. Remember, natural log of e, the 5r is going to come down, and natural log of e is 1, so that gives us that the natural log of 1.25 is equal to 5r. Divide both sides by 5. So the r, or the rate, is going to be the natural log of 1.25 divided by 5. And so we could plug that in. Natural log of 1.25 parentheses divided by 5. I get 0.0446. Incidentally, that's about a 4.46% growth rate, right? So that gives us that we can use this formula. A equals 20,000 e to the 0.0446. Oops. T. Let me just do 0.044. I'll go 0.045. I'll round it that way. T. And then now, the last part of the question, find the year 2008. Well, 1990 was year 0, so 2008, bless you, is going to be 18 years. So if we subtract these two, we find it's 18 years. So then plug in t equals 18 to that formula, or that function we got, and you'll have your answer. How's that? Helpful? Okay.